Hi, I'm Viktoria Boháčiková, Technical Product Specialist at Gexcon, and I would like to welcome you to our second chapter of video series Ammonia Hazard Modelling with Effects and RISKCURVES. In our first video, we discussed why safety is so important when working with ammonia. Today, we'll look at ammonia's unique properties and the hazards we need to manage. Let's start with what makes ammonia such a unique substance. Ammonia is a colorless gas or liquid with strong pungent smell that's noticeable even at very low concentrations. It has a boiling point of -33°C, allowing it to transition easily between liquid and gas depending on temperature and pressure. When released into the air, ammonia reacts with moisture, forming a visible mist or fog made up of ammonium hydroxide droplets. It is highly soluble in water, forming an alkaline solution that can be corrosive to certain materials. And in its liquefied form, ammonia has high thermal conductivity, making it an effective refrigerant for industrial applications. Now, let's look at how ammonia disperses after being released. Ammonia's dispersion behavior varies significantly depending on whether it is released as a gas or in its liquefied form, primarily due to physical properties and interaction with the environment. When ammonia is released as a gas, it typically disperses as a buoyant plume because ammonia is lighter than air. In open areas, the gas tends to rise and disperse upwards, reducing ground level concentrations. However, in confined or enclosed spaces, the gas can accumulate. Meanwhile, releases of liquefied ammonia involve more complex dispersion behavior. Pressurized ammonia rapidly expands upon release and partially vaporizes, forming a two-phase jet of vapor and liquid droplets. This process, which we call flashing, results in two-phase cloud. Initially, the ammonia air mixture can be denser than the surrounding air due to the presence of liquid droplets and cooling effect of rapid evaporation. This density difference causes the cloud to spread laterally near the ground before eventually becoming buoyant as it warms and ammonia droplets evaporate. In contrast, if cryogenic ammonia is released, most of the content rains out into a pool. The evaporating pool produces ammonia vapor. Now, let's take a look at ammonia hazards. The most significant hazard associated with ammonia is its toxicity. When inhaled, ammonia gas can cause severe irritation to the nose and throat. In extreme cases, it can lead to pulmonary edema, a life-threatening condition where fluid builds up in the lungs. Ammonia in its gas or liquid form can burn or freeze the skin, potentially leaving permanent scars. And ammonia is also highly corrosive to the eyes, potentially causing permanent damage or even blindness. The severity of exposure depends on both the concentration of ammonia and the duration of the exposure. This is why safety measures and exposure limits like AEGL, ERPG, or IDLH are important in managing ammonia-related risks. Also, ammonia is flammable at concentrations between 15 to 28% in air, and it has a high ignition energy and flash point. However, ammonia is unlikely to ignite spontaneously under normal conditions unless it has been significantly preheated. Therefore, fire and explosion hazards are not usually considered in ammonia safety studies. And finally, we must consider ammonia's impact on the environment. When released, ammonia vapor reacts with moisture in the air, eventually returning to the ground as ammonium. This can contaminate soil and water sources, harming aquatic life and requiring remediation. Proper containment and cleanup procedures are critical to minimize these environmental risks. Now that we understand ammonia hazards, let's break down the potential events that can occur during a catastrophic rupture or a continuous leak of ammonia. To help clarify this, I created a loss of containment diagram specifically for ammonia applications, which you can see here on the screen. Let me guide you through it step by step. If ammonia is released instantaneously as a pressurized gas or pressurized liquefied gas and does not ignite, the rupture will cause an overpressure effect. However, the mechanism will slightly differ depending on state of the ammonia. When a vessel storing pressurized liquefied ammonia bursts, rapid depressurization causes the flashing of a two-phase liquid and vapor mixture. This sudden phase change dramatically increases the volume, generating an overpressure and forming the blast vane. If the vessel contains only gas, the overpressure results solely from the expansion of the pre-existing vapor. This differs from blevane, as there is no additional flash vaporization. Additionally, fragments of the vessel can be propelled over long distances, creating additional danger for those nearby. Another important event to always consider during ammonia releases is the formation and dispersion of toxic cloud. Regardless of whether ammonia is released instantaneously or continuously, this toxic cloud poses a significant hazard. When ammonia is released, it is typically in its gas or liquefied gas state. When ammonia is released as a gas, it rises quickly because it's lighter than air. This helps it spread quickly in open areas. But when liquefied ammonia is released, it flashes, creating a dense two-phased cloud that stays close to the ground, creating a much greater risk. It can easily move into populated areas, putting people at a risk of toxic exposure. This is especially a scenario of concern in places with poor ventilation or high population density. These hazards emphasize the critical importance of ammonia safety. Understanding this risk is essential to identifying the most effective strategies for preventing and controlling ammonia releases. One powerful approach for achieving this is hazard modeling. By simulating various scenarios, we can predict ammonia's behavior, evaluate potential outcomes, and implement proactive measures to mitigate risks and enhance safety. Thank you for watching. I hope this video has provided you with clearer understanding of ammonia's unique properties and associated hazards. Stay tuned for the next part. We will discuss the challenges of modeling ammonia hazards. See you soon!